All right, so we're just warming up here and we're going to practice a couple of problems and then use this time for you guys to work together on solving some more of these. So this will be relatively short. But what I wanted to do here with you is run through a couple of examples. And just practice. It says find dy dx by implicit differentiation and evaluate the derivative at the given point. Okay, so we are evaluating. Now a couple of these are missing points, and so we'll just pick a point that we want to evaluate it at. If there's a point given. So let's look first of all at this one here. We have tangent of x plus y equals x. And when we have an equation like this, and we're trying to find the derivative of y with respect to x, what's kind of our process that we want to go through here?
So first, find the derivative of both sides.
Okay, good. We're going to take the derivative of both sides with respect to x. Okay, so if I do that in this case here, the left or the right hand side's easy, that's just 1. But now I have the left hand side, and what am I going to have to do to find the derivative of tangent of x plus y? Chain rule. Yeah, chain rule. So the outer function here is the tangent, and the derivative of tangent is secant squared. Secant squared, and notice it stays x plus y in the parentheses. Okay? Then I have to multiply that by the derivative of the inside. So what's the derivative of x plus y?
1 plus
Yeah, you guys are getting the hang of it. 1 plus dy dx. Anytime you're taking the derivative of something that's not an x, you take the derivative like you normally would and then multiply by dy dx, because that's the chain rule again, actually. All right, so the derivative of something to the first is just 1 times something to the 0, so it's just 1. And then we have that times dy dx. Okay? So at this point, what we need to do is simplify a little bit. How do I get a secant squared over to the other side? Okay, if I divide by secant squared, I've got a 1 plus dy dx equals 1 over secant squared. Now, what is 1 over secant squared?
cosine squared.
Cosine squared, very good. Secant and cosine are reciprocals, so I can rewrite that as cosine of x plus y. And then of course we just subtract the 1 here. So it's cosine squared minus 1, which is dy dx. Yes, Davi?
So you basically just take the derivative, then put the dy dx on one side?
Yeah.
Yeah. Oh.
Yeah. This is our whole process. We're going to take the derivative with respect to x. Anytime you're differentiating something that is not an x already, you put that dy dx on there. And then once you have that, you get everything that has a dy dx on one side, everything that doesn't have a dy dx on the other side, and then if you need to, keep going to solve for dy dx. By the way, what could we convert cosine squared of x plus y minus 1 into?
Sine squared of x.
Close.
Negative sine squared.
Negative sine squared, okay? Dy dx, we could say here is a negative sine squared of x plus y. Okay? Either way, notice when we go to evaluate the slope of the tangent line at the point 0, 0, we're going to get we're going to get a negative sine squared of 0 plus 0. And what's sine of 0?
1? Wait, no, I'm sorry.
That one's 0. Yeah, sine of 0 is 0. Or if we had done it up here, cosine squared of 0 plus 0. What's cosine of 0? 1. So you have 1 minus 1, which still ends up giving us 0. Okay, so either way, you'd end up with 0 as the slope of the tangent line. So that tells us that the point 0, 0 in this case, if we were to graph these out, we'd have either a max or a min or a plateau point. Okay, here's the thing. This one, we wouldn't necessarily graph. These are more geared towards applications to things that deal with rates of change. And actually that's what we're going to start on Monday, is dealing with related rates. And we're going to spend a good part of next week on that, and then we're going to have our test next Friday. Okay? So it's actually the unit test. All right, we just had a quiz. Next Friday, we'll have our test. Now, the cool thing with this is, all right, we're kind of having 2 tests on Unit 2.
Yes.
All right, you're going to have an in-class test, but then you're going to have related rates problems that are take-home, because sometimes those can take a little bit, and it's hard to gauge how long it's going to take you. So we'll talk about this more, but that's something that you'll be able to work on your own and submit those, and those will be summative as well, and it'll actually both count as test grades.
Wow.
So
Can you repeat that real quick, because I was reading some stuff?
now, by the way, this second one, part of the reason why we're skipping some of this, example 2 is just example 1 after we took the initial first step. So we're going to skip that. And in fact, we're going to skip all the way down. I'm not even going to show those. We're going to skip down to number 7. Okay? So let's skip down to number 7. All right? We want to find the second derivative of y with respect to x. Okay? So we're skipping down to number 7 on the second page. The second derivative of y with respect to x. So let's start out using the same process that we did. We're going to take the derivative of both sides with respect to x. Okay? So
it's not like respect to x squared, it's just respect to x.
yeah, the 2 is there. We don't really say with respect to x squared. We're still differentiating with respect to x, but the notation is there just to show the second derivative. So that's a good question. All right, so the derivative of the right-hand side is easy. That's just a 0. Okay? The derivative of the left. Can someone tell us what we would get for the derivative of the left-hand side?
2x plus 2y.
2x plus 2y dy dx.
Oh, yeah.
Okay? Good. 2x plus 2y dy dx.
Mr. Hickson,
Yes.
could you have organized it before you had started it? Like x squared minus 25 equals, no, y squared equals 25 minus x squared.
You
Could
can.
you have done
You can do that. If you do everything correctly, that simplifying or whatever won't make a difference in the end, but you can. Like for example here, if we want, we could divide both sides of the equation by 2. So let's go ahead and do that. Okay? So I'm going to divide everything by 2 and I get x plus y dy dx equals 0. Okay? Now, kind of on the side here, I'm going to show, I'm also going to find out what dy dx is, and you'll see why in a minute here, okay? So dy dx, I'm going to subtract the x from both sides, and I have y times dy dx equals a negative x, and then I know that dy dx equals a negative x over y. Okay? So that's the first part, but we're not done. We need to find the second derivative. Okay? Now, we could take the derivative of that before what we just did, or we can take the derivative of this. Which do you want to go with?
The first one, the one to the left, maybe.
The one to the left? Okay. All right, so we want to take the derivative again with respect to x. So the derivative, here we're taking the derivative with respect to x. To get from here to here, we did the derivative the first time. Okay? So let's go ahead and change colors. So we have the derivative of x, which is just 1. The derivative of 0, which is 0. But then we have this y times dy dx. So we need to use the product rule. Okay? So we have the derivative of the first factor, which is derivative of y with respect to x, times the derivative of y with respect to x, that second factor.
Yes.
Okay? So it's the derivative of the y, the first factor, that's where we got this dy dx, times the second factor. That's where we got that one. Okay? Then we have to add to that plus the first term times the derivative of the second term. Now, what's the derivative of dy dx? Not squared, but it's the second derivative, right?
Yeah.
The derivative of the derivative is the second derivative. So that's this. And that's what we're going to solve for.
One question.
Yes?
So isn't the second derivative is like the dash?
You can write it as, like, if you have y, you could make it y prime and then y double prime,
Yeah.
or f prime, f double prime, yeah.
But like,
You can use that notation. In the context of related rates and implicit differentiation, this notation is a little more common. So that's why I'm using that. And especially implicit differentiation, it doesn't matter as much. You'll see the primes and this. But when we get to rates on Monday, we definitely use this notation more often. So that's why I'm using it here. Okay, so at this point, let's do a little bit of substitution. Okay, I have 1 plus dy dx times dy dx. Well, I know dy dx is a negative x over y, right?
Yeah.
So I'm going to substitute that in. Plus y times the second derivative equals 0. Question?
Could you repeat how you got dy, why you put a dy dx times dy dx between the 1 and 1?
This was the first half of our product rule. The derivative of the first factor is the derivative of y with respect to x times the second factor. The second factor just happens to also be dy dx. So that's why we ended up with 2 of them.
Like a plus b squared, right?
Wait, like what?
I didn't find it.
Okay. All right, so now we need to do some simplifying here. We have, I'm going to go ahead and subtract 1. So that's going to be a negative 1. This is an x squared over y squared plus y So I'm going to subtract that as well. So y times d squared y dx squared is -1 minus x squared over y squared. And then I'm going to divide by y. So I'm going to divide both parts by y, and I'm going to get d squared y dx squared. The second derivative equals a -1 over y minus x squared over y cubed now.
Oh, I see.
Because I divided both of those by another y.
One and one.
Now let me just show you something here, because this can actually help a little bit. I'm going to change colors one more time here and go back to where we had dy dx. I told you could do it either way. Alright, let's think though about if we had taken this one and taken the derivative of that a second time. For one thing, the derivative of the left-hand side would have just been what we're looking for. So there's our second derivative. The right-hand side, what would I have had to use to get the
Quotient rule.
derivative there? Yeah, the quotient rule.
Yeah.
So low
D high.
d high, so the derivative of -x is just a -1 minus high d low. D low is dy dx all over low squared, so this is over y squared. Okay? So that gives us a -y plus x times dy dx. Well, we know dy dx is a -x over y, right? All over y squared. So that is, notice I'm going to split this into two separate fractions. I have a -y over y squared minus an x squared over y squared. And what do you know? That simplifies down to a -1 over y minus x squared over y cubed. Same thing we got. Which one's easier? I don't know. Depends on what you see. But that's the cool thing about math. You could do the same thing two different ways and you still get the same results at the end. Okay? Any questions about this?
Yeah. Does that mean you're recording or not?
Okay, one more example. Find the tangent line to the graph. So now we're not just going to find the derivative, we're actually going to do something with it. We want to find the tangent line to the graph at this point, root 2 over 2, root 2 over 2. Okay? So we need to find the derivative, get the slope of the tangent line, and then we can use that with the point to actually get the equation of the tangent line. Alright? So take a minute or two here, try to get the derivative of this on your own. Try to find what is dy dx. Okay? how are we doing on this? Do we have at least an expression for dy dx?
Might not be right.
That's okay. That's why we're practicing. It's not right yet. Maybe. All right. What did you have to use here on the left-hand side? Product rule. Yeah, product rule. So, whoops, wrong thing. There we go. All right, so now you can see what we have here. We have the product rule. Let me get a little bigger pointer so you can see it. All right, so we have the product rule. So the derivative of the x squared times this whole parentheses plus the original x squared times the derivative of the parentheses. And you'll see in there we had the dy dx that we had to include when we did the derivative of the y squared. Okay? So then we have the same thing on the right-hand side. We have a 2y dy dx as the derivative of y squared. Okay? Everyone understand up to that point? Okay? Now it's just algebra, guys. It's just algebra. I went ahead and I distributed the x squared to both parts of the parentheses. I also am going to distribute the 2x to both sets here. So I have a 2x cubed and a 2xy squared. But the reason I do that is so that now I can take this term that has the dy dx over to the other side. Okay? So I have now both terms that have dy dx's on the right. On the left here I have all of this part that did not have dy dx's. So I have a 2x cubed plus another 2x cubed is 4x cubed. I have 2x times y squared also added over here. Okay? Now on the right side, since both of these have dy dx's, I'm factoring it out. Okay? And then I can divide by this set of parentheses to get dy dx equal to 4x cubed plus 2xy squared all over 2y minus 2x squared y.
Is it possible for the dy dx's cancel out?
It should not. It should not.
So it will never.
If it did, there's probably something going on there.
Like
Like the derivative is undefined or it's not differentiable or something like that. I'm not sure. But I think if you're doing this, it's never gonna cancel out. Now, one thing that we can do to simplify this here, notice all four parts of this in this fraction have 2's in them. So the best thing to do here would be to simplify a little further. 2x cubed plus xy squared over a y minus x squared y. Okay, so that would be my final answer. Now here's the thing. The point of this is to get the equation of the tangent line. If that's the case, it doesn't matter how much or how little you simplify. You'll get there eventually. Okay? But since I simplified, my numbers stay nice and small, or smaller than they would be. So now I'm going to find the slope of my tangent line, which is the dy dx at this point. So I have a 2 times a root 2 over 2 cubed plus x, which is root 2 over 2, times a y squared, so that's a root 2 over 2 squared, all over y, which is root 2 over 2, minus x squared, x is root 2 over 2, times y, which again is root 2 over 2. So we have a lot of root 2 over 2's here. But notice now we can just simplify and find out what our slope is. Okay? So let's see, this is going to be root 2 over 2 cubed is going to be a 2 root 2 over 8, which is a root 2 over 4 times 2 is root 2 over 2. Plus square root of 2 over 2 times root 2 over 2 squared. That's going to be a 2/4 or 1/2. So that's going to be a root 2 over 4. Okay, so there's my numerator. The denominator is a root 2 over 2 minus, well, that's the same thing as what we had over here, so that must be a root 2 over 4 as well. Okay? So how are we going to simplify this?
Common denominator.
Okay, we could get a, what would the common denominator of all 4 of these fractions be?
8.
4. 8 would work too. Hey, 8 works, but 4 is a little smaller.
16 works.
Okay? Yeah, it doesn't have to be the least common denominator, it just needs to be a common denominator. But we'll go with 4. And let's go ahead and multiply the top and the bottom by 4, and that'll get rid of all of our fractions. And I'm allowed to do that because I'm just multiplying by 1, right? So now I have a 2 root 2 plus a 1 root 2 over a 2 root 2 minus a 1 root 2. So I have 3 root 2 over root 2. So my slope was just 3. So the equation, or the slope of my tangent line equals 3. And now, however you guys like to find the equations of lines, go for it, alright? So, now, change color one last time. I have y minus, not equals, y minus the y coordinate equals the slope times x minus the x coordinate. And I can get it into slope-intercept form. That's going to be 3x minus 3 root 2 over 2 plus a root 2 over 2. So that's going to be a minus 2 root 2 over 2. Or y equals 3x minus root 2. And there is the equation of our tangent line. You guys know how to do the algebra, but okay. So there's some application for us. We're going to do a whole lot more application starting on Monday with the related rates, but this is some basic application of our implicit differentiation. And guys, it's a lot of work. I recognize that. Okay, there's a lot of work in these, but if you just take it one step at a time, they're really not too bad. Okay? All right. Any questions?
No.
Okay.
Question.
Yes.
In the AP exam, like, do you get partial credit for your work on questions, or is it like, is it multiple choice?
On the multiple choice on the AP exam, no. It's just right or wrong. On the free response, yes.
Okay.
So, but that's why we're giving you some multiple choice. And as the year goes on, we're not always going to give you partial credit. Like some, you know how on the multiple choice on the quiz, some problem, they were all worth 40, but there were a couple of answers that were like right except they had the wrong sign, or they were really, really close. So we gave you some partial credit for having a better wrong answer, I guess you could say. That's not going to happen on the AP exam, and we're going to phase that out as well as the year goes on. So, okay. All right. So we've got some problems here to work with. 29 to 39 the odd, 45, 53, 57, 59, and 65. So I'm gonna give you the rest of our time to start that, ask questions and whatnot. Alright? There we go.